Welcome to the Resilience Advantage series, brought to you by the U.S. Resiliency Council and Optimum Seismic. I'm your host, Evan Reese. In this series, we're exploring what resilience means to the long-term sustainability of our communities in the face of natural disasters like earthquakes, hurricanes, floods, wildfires, and now even pandemics. Civil engineering is often considered the oldest engineering discipline. I mean, people were building buildings thousands of years before cars, airplanes, and computers. But that doesn't mean civil engineering and building construction isn't at the cutting edge of science and innovation. In this episode, we'll explore how engineers, researchers, and construction industry leaders have developed innovative solutions to make our buildings more resilient to natural hazards like earthquakes, and do it affordably. In the profession of earthquake engineering, experience is often the best teacher. This means learning what went right, and unfortunately also what went wrong when our cities are hit by large earthquakes. Thanks to science and innovation, instead of always chasing behind the last problem, we've learned to approach innovation from both directions, learning from the past and testing and modeling new designs for the future. And that has created new opportunities from which owners, businesses, and communities can now benefit. How this is being done and what these opportunities are what you'll get a taste of in this episode. The first advance we're going to talk about is the art and science of testing different structural systems and their components to better understand those that present the greatest risk and how to build better. Tara Hutchinson is a professor of structural engineering at UC San Diego, at the country's largest outdoor earthquake shake table. Tara, tell us a little bit more about what you do.
The lion's share of my research is in the general field of earthquake engineering. I'm an earthquake experimentalist, I would say, testing components, subcomponents, materials, and connections to try to better understand their performance under earthquake loads.
As I understand it, you can test full-scale mock-ups of buildings on your shake table.
You sure can. On our outdoor shake table, you can test a whole building on that outdoor shake table. You can test models of whole buildings on some of our indoor testing facilities.
Tara, why is it so important to do physical testing rather than just, say, modeling buildings on computers?
The reason why physical testing is such an important research tool for understanding the behavior of buildings and their components is largely due to the complexity of these structural systems. We can simulate or write a mathematical expression which might help us understand a beam, but that beam, when it's spanning from point to point, multiple points, or is clad or supports a floor system, becomes much more complex.
What kind of improvements to our codes and the way we design buildings has research like yours led to?
And ultimately, if we can model these systems to a greater level of precision, we can design them to a greater level of precision. So there is an indirect connection there, or direct connection there actually, to the improvement of design codes because the tools are improved for design engineers.
Where do you see physical testing making the biggest contribution to resilience in years to come?
One of the biggest challenges, I feel, is dealing with existing building stock. The engineering research community kind of needs to keep up with that and think of some more innovative strategies for rehabilitating and retrofitting these structures. And we talk now today as a research and practice community about functional recovery. We can't do that unless we address the existing building stock.
As impressive and useful as physical testing is, it can be expensive and will never be able to fully test the largest structures or how the full variety of existing structures might perform in earthquakes. Fortunately, with vast advances in computing, software and tools are now accessible to almost any engineer or researcher to test our theories and simulate designs much more economically at the desktop and with the computing power of the cloud. I spoke with one such researcher who is at the forefront of using computer power to help engineers design better performing buildings.
My name is Kurt Hazelton. I'm a professor at California State University, Chico, and I also founded a software company, Hazelton Baker Risk Group, with a professor at Stanford. And we focus on software to support resilient design of buildings.
When I started out in engineering back in the late 1980s, running a computer simulation of a building often took all night. Things are sure different now.
So we can run 5 to 10,000 simulations of how your building might be damaged in an earthquake. And that takes 2 to 3 minutes these days. We've actually run, resiliency assessments of all the buildings in the state of California, 13 million. And with all of the Amazon processors that we can spin up, that takes 4 days to run all of that analysis. So it's amazing how much that stuff has improved in the last approximately 10, maybe 15 years. And really is a game changer in being able to do this kind of computing and analysis.
How has computing kept up with engineering science and our learned experience in past earthquakes?
Over the last about 20 years, we've gone from being able to design buildings for safety objectives to being able to evaluate buildings looking at damage and looking at damage to individual components in the building, and doing that in a very complete way so that engineers can design to limit that damage and to get buildings to be functional more quickly after an earthquake.
A professor of mine once said, "Garbage in, garbage out." How do you verify that these sophisticated computer models reflect how buildings actually perform in earthquakes?
We do use earthquake data to make sure that we validate our predictive models. So one thing that we've done recently is we went back through and we estimated the damage and repair cost to all the buildings in Northridge in 1994. And we compared that to the Northridge experience data, both in terms of repair cost, but also in terms of the likelihood that a building will be closed, will be red tagged and deemed unsafe after the earthquake. And we found good agreement, and in doing so, we made some modifications to the method to tune some stuff up. And then now that we've done that, what we can do, since it's an analytical method, we can now forward predict using that same method to things that we don't have earthquake data for.
How are engineers using these software tools to design better buildings?
We now have the technology, right, or analysis capability to be able to do those designs and to be able to say, if you make these 6 design decisions to make the building better, the outcome is a building that is quickly regaining function after an earthquake.
Are engineers using this technology to retrofit existing buildings as well as for designing new structures?
Yeah, this is not scoped to only new buildings. In fact, probably most of the uses of this technology are for existing buildings. It's the common use case is an owner, right, wants to know what they're getting for their current building. Is it going to be functional after an earthquake or not? And the follow-on question often asked is, what can I do to make my recovery time faster? Right? What kinds of retrofits can I do? So this technology can be used for all of that.
Private industry innovators are also using physical testing and advanced modeling to create construction products and approaches that bring high technology cost-effectively to the job site. I spoke with 5 members of the U.S. Resiliency Council's Industry Partner Committee about how their companies are making better building performance more accessible.
My name is Alan Klemchek. I'm the president of Taylor Devices, structural products, and our products are used throughout the world to protect buildings and bridges from the harmful effects of wind and earthquakes.
Hello, my name is Kyle Wilson, and I work as a regional engineer for Side Plate Systems. So we created a patented moment frame design to be a direct solution to some of the design flaws that we as structural engineers found from those pre-Northridge moment frame connections.
My name is Blake Ross-Kelly. I am Senior Structural Engineer in Business and Product Development with Clark Pacific. Clark Pacific is a prefabricated building systems designer, manufacturer, and construction company. And we create building products out of primarily precast concrete.
I'm Brian Saxey. I'm the technical director for Core Brace. We are a manufacturer of buckling restrained braces. These are products that are used in buildings in moderate and high seismic areas to improve their seismic performance.
I'm Jeff Ellis. I am a licensed California structural engineer. I've been with Simpson Strong-Tie now for 21 years and manage our building code and product compliance efforts. Our company has been around since 1956. Providing solutions for the construction industry since then, starting out with wood connectors and evolving into all the way up through moment frames.
It's often in serendipitous ways that new technologies and innovations come about. In the construction industry, oftentimes we learn best from what went wrong in the past.
It's interesting to see how structural engineers used to design buildings back in the 80s and in the 90s, and what significant earthquakes have happened. SciPlate was developed in 1995, right after the Northridge earthquake. And from that significant earthquake, that's when we, as structural engineers, learned a lot of design flaws.
The kind of work that Tara Hutchinson and Kurt Hazelton do is also being done by private sector businesses, from startups to construction industry giants, who are testing and modeling the behavior of materials and new approaches before an earthquake does.
From a product supplier aspect, research and development activities, design and detailing software, manufacturing processes, all of these things have significantly changed. We've gone from manually running and measuring, small component tests to performing tests using advanced electronically controlled hydraulic testing systems.
The software changes have been equally as important. Over the last few decades, the technology has grown exponentially. But additionally, the fact that many engineers use similar or the same software codes for building design is a key contributor to helping us integrate better resiliency in our products into structures.
Buckling restraint braces are an element that is highly tested, highly researched, a lot of full-scale testing of analytical models. So this allows us to really understand how the building's going to perform and really optimize and tune the building for a specific performance that we're trying to get.
A lot of people may think concrete is a pretty low-tech material, but that isn't necessarily true, and it doesn't mean it's not resilient. Blake Ross Kelly of Clark Pacific explains this, and also how their innovative precast hybrid moment frame works.
In a seismic event, the mild steel bars are allowed to yield while the strong tendon remains elastic, meaning it doesn't yield. So like a rubber band, it will bounce back as the building rocks back and forth. And because it remains elastic, when the shaking ends, it will pull the building back into place so that it is vertical again.
It's difficult for the construction industry to overcome the inertia that often sets in with contractors wanting to use the older, tried and true methods they've been employing for decades.
So we started working with structural engineers, getting them educated on some of the engineering benefits that it can provide to a new structure. And then from there, we used and leveraged those structural engineers to influence general contractors that it can actually benefit their project as a whole. SciPlate is a very stiff connection. And so with that increased stiffness over a conventional moment frame design, we can actually reduce the overall amount of steel on the project from the steel beam and column sizes. And so that can equate to tens of thousands of dollars to maybe sometimes even hundreds of thousands of dollars, or even sometimes even $1 million worth of raw steel savings on a project.
Clark Pacific is a design build contract. The efforts that we go through are basically an education of our customer to let them know what the benefits are of a resilient lateral system and how the system performs in order to provide them with added value.
We offer a plethora of tools on our website for designers and installers and contractors, builders that are software type solutions, the ones that are on the desktop that can help you design cast in place concrete anchors or post installed concrete anchors, or design moment frames, as well as tools to make the process more efficient.
Working with SciPlate in the early development stages, we offer a lot of free tools and free services up front in the early stage design so that the building owners, the GCs, or the design team can better evaluate and have the better education to determine what's going to make most sense for their structure.
Sometimes innovation comes not from having a high-tech mechanical system, but just from finding a better way to do the things we've always done in the past.
Really, innovation can be as simple as a screw that works more efficiently and is more effective in doing its job. and that can bring efficiencies to the industry, as well as perhaps creating safer structures.
We've talked in past episodes about performance-based design, the ability to achieve building performance beyond the minimum safety provisions. The technologies offered by these companies make it easier than ever to achieve high-performing structures.
You can reduce the amount of time it takes to occupy that building after an earthquake. It can reduce the repair costs. It can help to actually even reduce the acceleration of the things, the people, and the equipment that are in that building. So the owners definitely have a choice to say to their engineers, hey, look, I want a better performing building. I want my building to perform better in an earthquake. What do I need to do to upgrade my building so I exceed code requirements? That is definitely a decision that all owners could face, and that our technologies can be provided to give you that higher level of performance.
Are your products used both in new buildings and in seismically retrofitting existing structures?
Fluid viscous dampers are certainly applicable to both new and retrofit structures, for sure. We have now have over 750 projects worldwide that incorporate viscous dampers. And because fluid dampers act like shock absorbers on your car, they operate and absorb energy only when they move.
When you are changing the occupancy of a building, going from a warehouse to a office use or something in the same building, if you're thinking about adding resiliency to the structure, that's a great time to do it.
In advancing the use of resilient design techniques, we have to address the situation and the needs of the building owner or developer. We return here to the case of the new Oregon Treasury building, currently under construction in the state capitol, that we first introduced in a previous episode. A lot of construction in Oregon uses traditional steel framing fixed to the building's foundation. But because of the essential functions that occur every day within the Oregon Treasury building, the project team decided to use base isolation to ensure that the building would be up and running after a major earthquake off the Oregon coast. Byron Williams, one of the project's managers, explains how the decision to use an innovative structural system was made.
The discussions around why base isolation provided that when steel did not really focused on what is the process that has to be used for that reoccupancy element. The base isolation enabled that the post-event review just to be completed much more quickly. For us to be able to say that we wanted to be operational after that earthquake, the building was no longer the bottleneck in the process.
How did you show that the additional cost of base isolation could be managed? Did you look at other projects for guidance?
Yes. So one of the pieces that we did is we retained DCW Consulting to do exactly that for us. That they, at each of the stages of the design process, that they were looking at other projects of similar nature in those elements. So looking at base isolated buildings, looking at steel frame buildings, or whatever various aspects we were looking at, and helping us perform some cost comparisons to make sure we understood the cost impacts of different decisions, but also the likely ranges that we were looking at kind of as we were just in some of those early discussions.
How did you communicate the building's expected performance in terms that the decision makers at the Treasury could understand?
So I think for me, one of the biggest tools that I used really was the USRC rating structure. Prior to really engaging with that model, I struggled to figure out how to articulate clearly the benefits and the different impacts. The framework really provided a mechanism to break it down into talking about damage to the building, the safety of the employees, and that recovery objective.
I assume that having a USRC rating also creates a level of consistency among engineers and the state going forward on future projects.
That science backing is really where it stands out, is that it's a lot of systems, they're more subjective in how they design those systems. And with the USRC system, the criteria were there that at some point you can hand it to, I could pick up from one structural engineering firm to another. For me, that was important. I want my outcomes to be repeatable by somebody else doing that analysis.
Innovation is a never-ending process, and the next generation of structural engineers and entrepreneurs are already thinking about how to improve the built environment. I spoke with Dr. Anahid Behrouzi, an assistant professor of structural engineering at California State University in San Luis Obispo, about how she is motivating her students to think about the future of resilience. She told me about one example, how Cal Poly's Earthquake Engineering Research Institute student chapter participates in a seismic design competition every year.
So the ERI Seismic Design Competition is an international competition. So they have to build a prototype balsa wood structure. It's about 5 feet tall. So what they do with that structure is they test it on a shake table. I do believe that this is one of those competitions that bridges the theoretical that they learn in the classroom with what is reality. We don't want them to be kind of in a bubble of academia. And it really resonated with them that, sustainability is not sustainable without resilience.
What are you doing to make sure students are skilled and ready to realize the possibilities when it comes to making our world more resilient?
We've talked a little bit about resilience from the design perspective when you're starting on a project, how building up that ability to communicate not just ideas, but having a similar resilience objective between the architect and the structural engineer is important. I think what we're trying to do here, at Cal Poly, but the relevance extends to industry, of course, is that we are trying to take kind of different silos of knowledge. We're trying to take architecture, we're trying to take new design, seismic design and other types of hazard design, but also this idea of retrofit and bring them together. In terms of resilience, we just don't have the luxury of time to figure this out later. I think it has to be a very kind of forward-thinking kind of approach.
Failure to invest in resilience now will cost us dearly in the future. But as experts in this episode have shown, the state of knowledge, techniques, and construction practices have advanced tremendously in recent years, making resilient design more possible and attainable than ever for both existing and new buildings. Engineers are at a pivot point in their capability to deliver a more resilient built environment, but they also have to communicate that capability and encourage demand and the follow-through from their clients and our communities. I hope you consider what all this means for you, your business, and your communities. You can watch or revisit other Resilience Advantage episodes that address other aspects of the resilience movement, such as the benefits of retrofitting. Our next episode goes deeper into the growing use of building rating systems as a tool for assessing, communicating, rewarding, and developing policies to increase resilience. Thank you for joining us on the Resilience Advantage.